So we'll continue doing exercise 236, and they're asking for three things. They're asking for whether each lone pair in a molecule is localized or delocalized. They're asking for the hybridization of the atoms they're on, and they're also asking for the geometry of the atoms they're on. So let's go to C. The first step is to draw in the lone pairs. So, and it might be a little easier actually if we draw this molecule with these bonds drawn out. So we'll copy that same structure. Just notice that the OH is really a bond between the oxygen and the hydrogen, and the NH2 is really two bonds between nitrogen and hydrogens. So now we'll just add the lone pairs on there, and so these lone pairs, the oxygen at the top right, that's going to need two lone pairs to get a total of 8 valence electrons. The oxygen to the left of it needs two lone pairs to get a total of 8 valence electrons, and each of the nitrogens needs just one lone pair to get a total of 8 electrons. So we'll want to go through these lone pairs one at a time to figure out whether they're localized or delocalized, and then see what their hybridization is and their shape. Okay, so let's look at these two lone pairs. Do those lone pairs fit any of the resonance patterns? They do. Those lone pairs are allylic. If you go one atom over, you're at an atom in a double bond. And so one of those lone pairs is going to be in a p orbital that's parallel with the p orbitals in that double bond. So it will be able to spread out. In other words, one of those lone pairs will be delocalized. It'll be on many locations, not just on one location. Delocalized. Notice the other lone pair can't also spread out there, because this, for example, this lone pair, in order for this to overlap with the other p orbitals, it has to be parallel with it. And so in this example, it would have to be in a py orbital, a p orbital going straight up and down. But each atom only has one py orbital. The others are px and pz coming out and going away from you. And if the other lone pair is in one of those orbitals, those are not parallel with the p orbitals in the pi bond, and so it wouldn't spread out through resonance. So only one of those lone pairs spreads out through resonance. Only one of those lone pairs is delocalized. That's what that was supposed to say, delocalized. The other lone pair is stuck. So this lone pair is stuck on the atom it's on, so it's localized. Okay, now if an atom has a delocalized lone pair at all, it is sp2 hybridized. It's using a p orbital. The oxygen is using this p orbital here in order for the resonance to happen. So it only has two other p orbitals left, and it mixes those with the s orbital, so it's sp2. sp2. And if an atom is ever sp2 hybridized, the geometry of the electrons around it is trigonal planar. And I'm saying the geometry of the electrons because there's a difference between electron geometry, where you treat lone pairs and bonds all like the same thing, as if they were all just bonds. That's electron geometry. And molecular geometry. That's where you really are just looking at the shape of the atoms, and so you treat the lone pairs and the bonds differently. So for 2, so that's localized. For the other one, the dark blue one, that's localized. The atom we already saw is sp2 hybridized because one of the p orbitals on that atom is being used for resonance. And so any sp2 hybridized atom will have an electron geometry of trigonal planar. Okay, let's clean that up just a little bit. Whoops. All right. So much for those two, for that first oxygen. Next, let's look at the lone pairs here. Do those fit any resonance patterns? They don't. They are not allylic. They're on an atom in a double bond, not one atom away, and they are not adjacent to a positive charge. There's no positive charge right on the atom next door. So there's no resonance patterns involved with those. That means that those are localized. They're localized. If you notice, though, that oxygen is involved in a pi bond, which means it's using a p orbital to form that pi bond. So it only has two p orbitals left to mix with the s, so it's sp2 hybridized. And as we saw a second ago, any sp2 hybridized atom will have a trigonal planar electron geometry. So that's that lone pair. Next lone pair, let's check out these lone pairs on the nitrogen there. And just for reference, I'll keep these circled in their respective colors. Okay, lone pairs on the nitrogen there. So are those lone pairs involved in any resonance patterns? And they are not. They're not allylic. If you go one atom over, you don't have a double bond, and they're not next to a positive charge. That same atom one over doesn't have a positive charge. So because it's not involved in resonance at all, those lone pairs are localized, and that's all there is to it. Now that means that atom, that nitrogen, doesn't need the lone pairs to be in a p orbital. Right? It's only when it's in resonance that the lone pair would have to be in a p orbital. So that nitrogen can mix all its p orbitals together. So it would be sp3 hybridized. Okay, now there's something you'd want to be careful with here. I would accept two shapes here. For the electron geometry, that's just looking at the electrons around an atom. You're making no distinction between lone pairs and bonds. You just assume all electrons push against each other equally. In that case, we would have 4 regions of electrons around the nitrogen, and it would be tetrahedral. So the electron geometry tetrahedral matches with the sp3. The molecular geometry, that's what the atoms look like when you treat the lone pair as something that's invisible, and you just look at the shape of the atoms when the lone pair and the bonds push each other away. The molecular geometry is what you would have predicted in chapter 1. 3 atoms, 1 lone pair, that would be trigonal pyramidal. So if you put either of those shapes for this one, I would completely accept it. Either one is technically a geometry for that atom. It's just one is an electron geometry, and the other is a molecular geometry, the geometry of the atoms, whereas the other is the geometry of just the electrons around the atom. So those are both the case, and if you notice, the other nitrogen is in the exact same case. It's not involved in resonance, right? It's not allylic, it's not next to a positive charge, so it's localized. Because there's no resonance, there's no need for that nitrogen to have a p orbital. Right? It's not in resonance and it's not involved in a pi bond, so there's no reason for it to have a p orbital. So it can mix all 3 of its p orbitals with the s orbital. It's sp3 hybridized. And the electron geometry would be tetrahedral, the molecular geometry, trigonal planar. So that's that one. Quite a few lone pairs in that one. Let's just do D. We'll add D to this. Now, none of these carbons in D have a lone pair, because none of them have a negative charge. But the nitrogen has 1, 2, 3 bonds drawn. So it only has 6 electrons. It needs 8. So we're just going to draw 1 lone pair in there. And this will give us an opportunity to talk about something that's kind of interesting. You might at first glance feel like this lone pair is allylic. And technically it is allylic. If you go 1 atom over, you're at an atom in a double bond. And up till now, we've said that allylic lone pairs cause resonance. And they almost always do. The one exception is if the lone pair is on an atom that has a conjugated double bond. Because think of what's happening with that conjugated double bond. Let me put these in a slightly different position. Let me put them right here. in order for the molecule to have a pi bond here, it has to have two p orbitals, one on this atom and one on that. And it's because those p orbitals are parallel with the p orbitals all around the ring that there is that fifth pattern of resonance in this molecule. The electrons in any of these pi bonds can go around the whole molecule. Okay, but notice all of these p orbitals are py orbitals. So if to form this pi bond, you're using your py orbital, that means you only have a px and a pz orbital. So if this lone pair tried to fit into a p orbital, it would have to be in a px orbital, and notice that that is not parallel with these, and so wouldn't let the electrons spread out, or in a pz orbital, also not parallel with these, and so wouldn't let the electrons spread out. So although these lone pairs are allylic, this lone pair is allylic, it is not able to spread out into these orbitals because the py orbital is already being used for this double bond. Okay, because this nitrogen does have a p orbital on it in order to make the pi bond, it only has two p orbitals left, so it's sp2 hybridized. Oh, and I should say, these lone pairs right here, those are localized. We just saw that they can, even though they're allylic, there's not another py orbital for them to fit into that could align up in a parallel way to allow it to fly into the other p orbitals, overlap with them. So it's localized, it's stuck there. We saw that that nitrogen is sp2 hybridized because it's just using one p orbital for the pi bond, and that means that the electron geometry around it will be trigonal planar. That's the electron geometry around it. And so that lone pair there, you can imagine there being three sp2 orbitals. One is going to make the sigma bond there, one is going to make the sigma bond in the other direction, and the third would be making the sigma bond, or would be the one that the lone pair would exist in, sort of pointing out at you if the p orbitals are going up and down. So I just wanted to point out that although that's allylic, when you think about the orbitals on that molecule, you see that it actually can't spread out into other parallel p orbitals, and so it's localized, it's stuck on that nitrogen. Also, the significance of something being localized means that the charge is stuck in a small place, and so it's more reactive. When you delocalize something, when you spread the electron's charge out, the charge in any individual place is smaller and more manageable, so the molecule becomes less reactive. So localized, more reactive; delocalized, less reactive.